here we're going to do a quick review of significant figures. So significant figures, we're looking at how it's going to apply in our biotech class. So first of all, we need to look at two different concepts. So there are two kinds of numbers. There are numbers that are exact numbers, and then there are measured numbers. When we're talking exact numbers, they do not come in fractions or decimal formats. You can't have a fraction of a human. You can have a fraction of a bacterial colony on a petri dish. They are exact numbers. They're indivisible into fractions or decimals. Therefore, significant figures are irrelevant in this case. On the other hand, sometimes you can have to approximate, and this is what we consider measured numbers. So measured numbers, using a tool device to measure, you must ask yourself, what are the limits of that tool or device? And then we're going to have to do some estimating if it's an analog tool, and if it's a digital tool, then we have to understand the limits of that digital tool. So examples, we have a centimeter ruler and we have millimeter rulers. So if we look at the centimeter ruler, we can see that that line is a little bit less than 4 centimeters, so maybe 3.9 centimeters. Now, some mathematicians might say 3.9 centimeters or 3.90 centimeters. They consider that possibly the same, but in science, it is definitely not the same. So that brings us to the concept of uncertainty. Now, there's a lot you can learn about uncertainty, and there are different sophisticated levels of uncertainty. We're going to keep this very simple for the biotech class. So if a centimeter ruler was used, then we would say the uncertainty is 1/2 of the smallest certain unit. In this case, our certain unit is centimeters. So we could say that line A, go away, is 3.9 centimeters plus or minus 0.5 centimeters. And line B is 3.4 centimeters plus or minus 0.5 centimeters. Now, sometimes you might say, well, what if I wanted to say plus or minus 0.1 centimeters? Well, if you think that you can visually divide it by tenths, great for you. But we're going to keep it really simple in biotech class. When you're in physics, you can go into more sophisticated determinations of your uncertainty. We always record the uncertain digit. In this case, the estimated digit read by eye on an analog tool. Now, if it were a millimeter ruler, then we could say that A is 39.1 millimeters plus or minus 0.5 millimeters, and arrow B is 33.8 millimeters plus or minus 0.5 millimeters, because we can see between the millimeter lines, and therefore we can estimate to the tenth of a millimeter, whereas in the centimeter ruler we could only measure to the tenth of a centimeter. Now, electronic devices I briefly mentioned. So the most common one we deal with in biotech is our balances. Our balances in our biotech class go to the hundredths place. Now, obviously, you can't estimate beyond the hundredths place. So the hundredths place, the last number on a digital readout, would be our uncertain digit. Now, many balances and many electronic devices have published uncertainty, but if you do not have access to the published uncertainty, then go with the largest possible, or the quote-unquote rounding possible. So we're going to say our balances go to plus or minus 0.05 grams. Now, if you were to go into our chemistry room, we have balances with much less uncertainty, but we are not using those regularly in biotech class. Okay, so let's look at the basic sig fig rules. Now that we know that exact numbers have an infinite amount of sig figs, so we don't even have to consider it because you cannot have fractions or decimal places, but measured numbers always have sig figs, and the sig figs are based on the limits of the tools we use to obtain those measured numbers. So basic decimal rules. If there is no decimal, then you start counting at the first non-zero and you stop counting at the last non-zero. So 30 has 1 sig fig. Right here, 1 sig fig. 303, 3 sig figs. 3030 has 3 sig figs, because this could be anywhere from, say, 3025 to 3034. If there is a decimal, then start counting at the first non-zero and count until the end. So 3.1, 2 sig figs. 3.03, 3 sig figs. 3.030, 4 sig figs, because we know not to the tenths, not to the hundredths, but we are clear to the thousandths place. And then 0.303, that's not significant. These three are. So test yourself. I'll give yourself a moment. Check yourself. Could you get the correct number of sig figs? It's that one. Could you get the correct number of sig figs? It's that one. 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 How about try these? 2 sig figs. 2 sig figs. 4 sig figs. 3 sig figs. 3 sig figs. 4 sig figs. And again on this last one, so that's thousands, millions, billions. So we know to 7 billion and 83 million. So it could be 7 billion 82.5 billion to 7 billion 83,400,999,999, etc., etc. As long as you don't hit the point where you'd round up to 7 billion 84 million. And I wish I knew what was up with the software, but moving on. Okay, let's check yourself again. Significant. Okay, so now we're looking at the uncertain number, which is what I was trying to explain in the last slide at the very end. How many significant figures here? Check yourself. All 4. Next one. Just these 2. Next one. All 5. Remember, the decimal place rule. All 3. Again, the decimal place rule. 3. These 3 because none of these are significant. 6. To here. The rest of this just tells us that we are dealing not with thousands or millions, but billions. Uncertainty. And again, remember these uncertainty rules are super simplified for biotech. In certain classes, you can go to a much greater sophistication level, but we're just introducing the concept of uncertainty. Okay, adding and subtracting. This is where students most often go wrong. So when adding or subtracting measured numbers, the answer can have no more places after the decimal than the least of the measured. So, for example, we see 2.45, so that takes us to the hundredths place, but 1.2, that only takes us to the tenths place. So that could be anywhere from 1.15 to 1.249999999. So even though our raw answer is 3.65, when we get to significant figures, we have to limit ourselves to the tenths place. That's our uncertain digit, and it's limited by going back to the origin of the material we were dealing with in the question. Okay, so again, now we only know to the ones place. So even though here's our raw answer, we are not certain about the thousands, we are not certain about the hundreds, we are not certain about the tenths. None of those. Okay, so we have to limit ourselves to the ones place. And weirdly, yes, it is the ones place that is uncertain. When you only have 1 sig fig, you get a lot of room for uncertainty. Multiplication and division. So when multiplying or dividing, the result can have no more significant figures than the least reliable measurement. So here's a couple examples. So 56.78 times 4.53. So we have 4 sig figs and we have 3 sig figs. Okay, and so here's our raw answer. Our raw answer, then we going to sig figs, we round to 3 sig figs. Again, that goes back to the fundamentals of what really multiplication is. We are multiplying 56.78, adding it to itself 2.45 times. Going back to basic 4th, 5th grade multiplication concepts. Uncertain digit, the ones place. Okay, so try this one. Do the math, and it rounds to which digit's uncertain. Can you do that? How would you record the uncertainty? So here are some quick, simple rules for reviewing adding and subtracting and multiplying and dividing. If you can do those, that gets you through the fundamentals of sig fig math for biotech. And again, when you go into physics or other higher math where you're doing a lot more mathematical manipulation, then you would have to learn more sophisticated rules. But this is just an introduction.